The hidden science of the perfect cut, manufacturing engineering, mechanical engineering. Let's get right into it.
You know, we're surrounded by objects made of metal. Everything from the phone in your hand to the engine in your car. And we totally take their precision for granted. But the process of making them, it's not gentle. It's this incredible, kind of violent science that's all happening at a microscopic level. I mean, really think about it for a second. An airplane wing, a surgical scalpel, a tiny gear in a race car engine, these aren't just any parts, right? These are components where one tiny microscopic imperfection could have absolutely catastrophic consequences. That kind of precision doesn't happen by accident. It's the result of an incredibly controlled process. So here's the secret. It's not about adding material the way 3D printing does. Nope. The most critical, high-strength metal parts in the world are made by starting with a solid block of metal and then scientifically carving material away. This is the world of subtractive manufacturing. Okay, so it really boils down to two main philosophies. On one hand, you've got additive manufacturing. We all know it as 3D printing, which builds parts up from nothing, layer by layer. It's amazing for prototypes and really complex shapes. But then you have subtractive manufacturing, or machining. That's where you start with more than you need and carve it down to the final shape. This is what gives us the unbelievable strength and precision needed for the most demanding jobs on the planet. And that second one, that's what we're diving into. So let's zoom in, like way in, to the exact moment a cutting tool makes contact with metal. What is actually happening when you make a single cut, or what engineers call making a chip? And the word in here is super important. This isn't just cutting. The term is severe plastic deformation. The tool isn't slicing the metal like a knife through butter. It's applying such an insane amount of force that the material in front of it literally fails along a very specific plane. That's the shear zone, and peels away. It's basically a controlled, super fast structural failure. Wild, right? You know, the crazy part is how that metal fails tells you everything you need to know about the quality of the cut. The chip itself is a report card. A long, smooth, continuous ribbon coming off a ductile material like steel, that's an A+. It means things are going great and you're getting a beautiful finish. But if you're cutting something brittle like cast iron, you get these little broken, discontinuous chips and a much rougher surface. And then you get the problem children, the built-up edge, which is a sure sign of trouble. And the serrated chip, which you see all the time when machining tough aerospace alloys like titanium. Yeah, that built-up edge, or BUE, this quote here really nails why it's so bad. The heat and pressure get so intense that tiny bits of the workpiece literally weld themselves onto the cutting tool. Then, that little welded-on piece breaks off, damaging the tool and smearing itself all over your brand new, supposedly perfect surface. Bottom line, it just ruins your surface finish. So, if the actual cut is that violent, you have to ask, what in the world can a tool be made of to survive that? This brings us to the cutting tools themselves. And trust me, they're total marvels of material science, engineered to survive right there at ground zero. You know, you can basically track the history of modern manufacturing by looking at the history of the tools themselves. We started with simple carbon steel, but it got soft as soon as it heated up. Then a huge leap with high-speed steel around 1900. But the real game changer was tungsten carbide. It was so much harder, letting us cut way faster. And that brings us to today, where the vast majority of all cutting, maybe 80 to 90%, is done with these super advanced coated carbide tools. And this right here, this is the fundamental challenge, the core problem in designing any cutting tool. You need it to be hard, so it doesn't wear down, but you also need it to be tough, so it doesn't just shatter. And those two things are usually opposites. Think about it. A diamond is incredibly hard, but it's brittle. You can shatter it. A rubber ball is really tough, but it's not hard at all. Somehow, a cutting tool has to be both. And it's not just about what the tool is made of, it's the shape of it. The geometry is everything. Take the rake angle, for instance. That's the angle of the cutting face. A positive rake angle gives you a sharp, knife-like edge. It slices beautifully through soft stuff like aluminum. But you try that on some tough cast iron, that edge is going to snap right off. For that, you need a negative rake angle. It's a much stronger, more robust edge that's built to take a beating. So how did engineers finally crack this code, this hardness versus toughness problem? Well, they kind of cheated. They decided not to choose one or the other. Instead, they figured out how to combine them using incredibly advanced coatings. This was the breakthrough that lets us machine faster and better than ever before. Okay, so check out how a modern tool is built. It's all about the layers. You start with a substrate, a tough carbide core that can take a punch and resist shock. Then you add an incredibly hard coating on top of that, like titanium carbonitride to fight wear. But the real genius move is that final layer, aluminum oxide. It's a thermal barrier. Its entire job is to keep heat out of the tool and force all that energy to leave with the hot chip. It's literally a microscopic heat shield for the tool. Okay, so we've got these incredible, high-tech, layered tools. Let's put them to work in a super common, real-world job, making one single, perfectly precise hole. So you start with a plain old drill bit. This gets you a hole, sure, but it's not very accurate. A drill bit can wander a little, and you might end up with a tolerance of plus or minus 1/10 of a millimeter, which for high-precision work is, well, it's pretty sloppy. All right, next up, boring. A boring tool comes in with a single cutting point. Its job is to enlarge the hole, make sure it's perfectly straight, and get the diameter much closer to the final size. Just this one step can literally cut the error in half. Pretty good. But to get it perfect, for that final sizing and a beautiful surface finish, you bring in the reamer. A reamer is designed to remove just a tiny, tiny amount of material to bring the hole to its exact final dimension. And just look at that tolerance. Plus or minus 1/100th of a millimeter. We're talking 10 times more precise than that first hole we drilled. That's a huge jump. And look, the order here is absolutely critical. You drill first to make the rough hole. Then you bore it to fix its position and make it straight. Then you ream it to get the perfect size and finish. And only then, when the hole is just right, do you come in with a tap to cut the threads. See, this isn't just a random list of steps. It's a hierarchy of perfection. Each tool comes in and fixes the little imperfections left by the tool before it. This step-by-step progressive correction is exactly how you get from a rough block of metal to a part you can trust in a jet engine. But wait, the tool and the process, they're only two pieces of the puzzle. To really master this, you got to control the whole environment. And that brings us to some really important supporting players. Let's talk about cutting fluids. You know, the coolant that's always getting sprayed everywhere in machining videos. Turns out it does way more than just cool things down. I mean, yes, cooling is vital for keeping the tool hard, but it also lubricates the cut to stop that nasty BUE from forming. It physically flushes the chips out of the way so they don't scratch up the surface, and it stops the shiny new metal from immediately starting to rust. And of course, not all fluids are created equal. You've got to pick the right one for the job. If you're cutting at super high speeds where heat is the #1 enemy, you go with a synthetic for max cooling. But for slow, heavy cuts where you really need to reduce friction, you'd pick an oil for its lubrication. And for everything in between, you've got emulsions that give you a nice balance. And really, that's what brings this whole thing full circle. Making a perfect part isn't about one magic bullet. It's all about controlling the entire system. It's about understanding the physics of how a chip is made, picking the perfect tool material and shape, and then bathing it all in the right cutting fluid. It's this constant, delicate balancing act between quality, speed, and cost. So the next time you pick up a perfectly smooth medical instrument, where you look at a simple threaded metal bolt, you'll know it didn't just appear that way. It's the end result of this incredibly violent, microscopic, and beautifully controlled science. Now that you've seen the invisible science behind it all, what everyday objects are you going to look at a little differently?